Okay, so this is the second video on conditional probability. It'll probably be the last one, but we will see. Going to look at the actual formula for conditional probability. It is in the formula book. I'll get to that in a second. I'm going to use a Venn diagram to kind of really show this very clearly. So I've got a Venn diagram here, and I've got a box around it, and I've got events A and B, and they've got some overlap here. So if I wanted to work out the probability of A given B, then the formula is this. It is the probability of A intersect B divided by the probability of just B. And I always think about it as it's the second one. So whatever's second here is what goes second. It goes on the bottom here. Now, why does that make sense? Why does that make sense? So we know B is happening. We know B is happening because it's given that B. So we know that we are in here. B must have happened. So actually, in a sense, we've changed. Instead of E over the entire world, we're now just in this section. We're just in this section. And we want to say out of these times, so out of these times, when does A happen? Well, A happens here. So it is this part, the intersection out of that. So it is just the intersection, which I'm going to need to colour twice to get that green colour. It is just the intersection out of the total. So we get that fraction. So it's that divided by that. This part out of this part. That's how to see it on a Venn diagram. Now, actually, it can be rearranged. We can multiply both sides, and we can see that it becomes the probability. And actually, I'm going to check it matches this of B multiplied by the probability of A given B is equal to the probability of A intersect B. If you compare this to, so this is if it is dependent now, because we don't, conditional probability, like the probability of A changes the probability of B. So this is when it is dependent. If we compare that to what happens if it's independent, well, if it's independent, we have the probability of B multiplied by the probability of A is equal to the probability of the intersection. So this is yet another way to show that if these two things are equal, then we have independence. So it shows that if probability of A given B is the probability of A, then these two formulas become the same and we have them this equal. Now, let's just have a quick look at what's in the formula book. This is what the formula book looks like. The most important thing that I say right now is this is not a formula you need. It's a bit confusing because it does have A given B on this left-hand side, but this is not necessary. You don't need this one. We've come across this one before. This one should be fairly obvious, and this is the new formula. But note, it's given it slightly differently. So it's written the probability of A intersect B is equal to the probability of A times the probability of B given A. I recommend you often think about this as the rearrangement of this formula, which is the probability of B given A is equal to the probability of A intersect B divided by the probability of A. And the letters are a different way around to what I did before, but note that the second one is on the bottom. And that's the same idea. Now they're very kind. They also give you these things which we discussed before. These are the checks for independent. And that means that if these things are true, you can say they're independent. So let's have a look at an example. So I've got two situations here. I've got A and B on this side and C and D on this side. So I'm actually going to do the questions 4 to 7 before I do questions 1, 2, and 3 here. So the probability of A given B, that is the probability of A intersect B divided by the probability of the second one, which is B. So what do we have? A intersect B, I can see on the left-hand side, is 0.1. And the probability of B is 0.1 plus 0.1 is 0.2. And so I can see that this is a half. Probability of B given A, that's the probability of B intersect A. It's the same as A intersect B, divided by the second one, which is the probability of A. This is going to be, well, the intersection again is 0.1, but the probability of A is 0.5. 0.5. So this is 1 out of 5. So are A and B independent? Well, let's have a look. What is the probability of A? The probability of A is 0.5, or a half. So this does equal the probability of A. And the probability of B is 0.2, which is that. So that is the probability of B. So are A and B independent? Yes. Probability of A given B is equal to the probability of A, because we just shown that over here. We could have actually have shown it also by saying that the probability of A times the probability of B is equal to the probability of A intersect B. So let's just double check that quickly. So that is probability of A is 0.5, probability of B is 0.2. I'm kind of slightly constrained for space here, so I'm going to do it up here. The probability of that is, probability of A is 0.5. Probability of that is 0.2. 0.5 times 0.2, does it equal the intersection? The intersection was 0.1. Yes, it does. So you could show that. Right, let's carry on with these. C given D. Let's look on the right-hand side. So this is an independent situation. A and B are independent. Probability of C given D. So the probability of C intersect D divided by the probability of D is equal to the intersection, 0.2, divided by the second one, it's 0.6, so this is a third. Probability of D given C, the probability that D happens given that C happens, is the intersection, D intersects C, divided by the second one, the probability of C, which is equal to 0.2, divided by the probability of C, which is 0.5, which is 2 out of 5. This, though, as we can see, this does not equal the probability of C, which equals 0.5. And this does not equal the probability of D, because that equals 0.6. So we can see, are C and D independent? No. Probability of C given D does not equal the probability of C, and that's all you'd need with working that I did down here. The last question on here says, are A and C independent? It's a bit of a cheeky one, so just to say that that is dependent, because they're in different Venn diagrams. A and C, A is here, C is here. So you might be tempted to say, yes, they're independent because they're in different Venn diagrams. But actually, the answer is, we don't know. We don't know. We don't know if they're actually in the same situation. They're definitely not presented in the same situation here, but they could, at situation 2, 1 and 2 could be the same situation. So the answer is we don't know. We would need more information. They might be, they might not be. Okay. So if you'd have been in the lessons before, you would see we kind of created this screen, which is an overview of kind of everything that we've got going on up to this point. But there's a few spaces missing, so let's fill them in. So on the left-hand side, we've got independence, as whether one thing affects another or not. So if they are independent, we've got this formula, which we've seen before, you've seen at GCSE. But we know that's only if they're independent. I'm going to add to this these other two things that we now have, which is that the probability of A given B is equal to the probability of A if they're independent, and also the probability of B given A is equal to the probability of B. But we can now add if dependent. Now, if they are dependent, we get a very similar formula to above, but it's now this formula instead. And I'm going to make sure it matches up with the way that it would be written. So the new formula, if they are dependent, is this. The probability of A multiplied by the probability of B given A. And it's quite often rearranged to look like this. The probability of B given A is equal to the probability of the intersection divided by the probability of the second one. Recapping on the right-hand side, I'm going to just show that for a second. Just leave that on the screen. But that is in the formula book. Mutually exclusive is a completely different situation. People sometimes kind of get these two things confused. But if they are mutually exclusive, then we know that the union is just the two things added together. In particular, it's because there is no intersection. And if they're not mutually exclusive, then we have this formula, which I did run through in class. And that is that the union is equal to the probability of A plus the probability of B minus 1 of the intersections. So if I have a Venn diagram like this, see the intersection's gone green, then the probability of the union is equal to the probability of A plus the probability of B minus 1 of the intersections, because it would double count the intersection. We would get two lots of the intersection, because if I took A and B, I would have two lots of the intersection, so I've got to take away one of them. And overall, you will get the probability of the whole thing. It should look something like that. So the probability of the whole thing with only one intersection is A plus B, take away one of the intersections. And we covered that before, but there are some questions on that. Right, I'm going to do an exam question now. And it's this one. Very typical looking exam question. It's got some information at the top and it immediately asks you to draw a Venn diagram. Pause the video now if you want to have a quick look over it. So I'm going to draw a Venn diagram. So I'm going to put my box around it. Always make sure I have a box on my Venn diagram. I'm going to have the two circles like this. So I'm going to call this A, I'm going to call this B, and this is my everything. So what bits of information do we have? We need to be really careful to kind of very carefully think about what bits of information we have already, what bits that we don't, and what these different things mean. So what does A intersect not B? mean? Well, that means it is in A, but it is not in B. It is in A, but it is not in B. So which part of the Venn diagram is this? So this part is in A and not in B. This part is in A and B. So therefore I can see it is this part. It is in A and it is not in B. So I know that this part is 0.32. So the intersection of B with not A. So it is not in A, but it is in B. So that must be this part here. Finally, we know that the A union B is 0.65. So that means that 0.32 plus 0.11 plus the intersection, this bit that we don't know yet, the probability of A intersect B, must be equal to 0.65. So if I take 0.65, so that means that the intersection must be equal to 0.65 minus 0.32 minus 0.11, which is 0.22. So this must be 0.22. Now finally, we want this bit outside of, so neither A nor B. So we are going to need to know that it all adds up to 1 and find out what's left. So I know that the probability of A, not A, intersected with not B, that's the outside, is going to be 1 minus 0.65, because that is the total of A union B. So it's the bit on the outside. And so I can see that that is 0.35. So this is 0.35 and my Venn diagram is complete. So write down the value of probability of A and probability of B. Well, the probability of A is 0.32 plus 0.22. So it is equal to 0.54. The probability of B is equal to 0.11 plus 0.22. So it is equal to 0.33. Okay, find the probability of A given that not B happens. Now there's two ways I can go about it. I can either go about it using the formula. So A given not B is equal to the probability of A intersect not B divided by the probability of the second one. It's kind of slightly more complicated to go about it this way because you've got to really carefully think about what these things are. There's no reason why we can't do that. In fact, we already have the top from the question. So this is 0.32. And not B, well, we know B is 0.33, so this is 0.67. And so this is 32 over 67. But we could also look at this in here, and I can see that not B is this part and this part, and A is just 0.32. So another way of looking at that is that I could say it is 0.32 divided by 0.32 plus 0.35. But that's kind of definitely, you get the same thing. So you could look at it in either way and get the right answer. So the final question here, it says, is determine whether or not A and B are independent. So we've got various different things that we could check here. And there are lots of different things. So I could either do the probability of A multiplied by the probability of B and see whether that is the intersection. So I think I am going to do that one. That's not bad. So because I've got A and B from part B. So probability of A times probability of B is 0.54 multiplied by 0.33, which is equal to, on my calculator, 0.1782. And this And probability of A intersect B, this would have to be equal to this if we were independent from the formula, but this is 0.22. So this does not equal 0.22, which is equal to the probability of A intersect B. So that's very clear. I've shown my working, and I can say that they are not independent. So note at this point, if I had this information already, I could have also shown that probability of B given A is not equal to probability of B. So this is other options in part D. Or I could have also shown that the probability of A given B is not equal to the probability of A. So that would be another option. And that is that exam question. So let's move on to another quick thing to talk about, which is on a tree diagram. So tree diagrams are actually pretty easy in terms of conditional probability because you've actually always been doing conditional probability on a tree diagram. I spoke about this in class as well, but just to kind of show that if we had two different things that could happen, and then you can either have A or B. So sorry, actually, that's not correct. So if you can have two different things that happen, first A happens and then B, two events, maybe you're flipping a coin and rolling a dice, or maybe one thing's happening after the other. You're taking a card out of the deck and not putting it back. Then we had A or not A as the first branches, and then B or not B as the second branches. And actually, you've already seen these probabilities, conditional probabilities on here, because the probability here is the probability of A, the probability here is the probability of not A. So this probability is that B happens given A happened. So this is the probability of B given A. And this is the probability of not B given A. Here is the probability of B given not A. And here is the probability of a not B given not A. So you actually have already been doing conditional probabilities for a while whenever you've done tree diagrams, and you know that you either put the same probabilities, so this probability and this probability are sometimes the same and sometimes they're not the same depending on whether they're independent or dependent. So you've seen situations like that before, like with or without replacement. So there is quite a lot of work to do to kind of really make sure you feel happy about these questions, and there's a lot of worded questions as well that you might need to kind of really think about, and obviously you can get help if you need them. But here's some suggested questions that I think you should work through, and that does cover the whole chapter, but do take your time really carefully reading the topic, reading the kind of worded questions as you go along. Okay, thank you.